All right, so we look at objects that are going to fall. Right, it'll probably be the first look at. Let's just take an object that's going to start at an initial position of 5 meters. We'll drop it. It'll end up on the ground with a final position of what?
0.
0. Do I have to make those labels? +5 as initial and 0 as final?
Yes.
Could I say this is 0 and this is -5? Be the same thing, right? Numerically, I would get the same values, right? But by convention, almost, the ground is going to be 0 for the most part. All right, so we'll let my final position be 0. My initial position be 5 meters. My initial velocity, when I let it go, how fast is it going? How fast is it moving? Should be 0 meters per second. My final velocity when it hits the ground, do I know what that is? I don't have any idea. The time it takes to hit the ground, any idea? How fast is it going to be accelerating or changing velocity? Or is it going to change the velocity? Is it just going to float there?
No.
So it's going to be changing velocity. How rapidly will that change occur? It'll occur with a magnitude of 9.8. Should it be positive or negative, or does it matter?
Negative.
Negative 9.8 meters per second. And that's it. It's all the 6 quantities I have. Is everybody good? Could I let my initial position be 0 and my final position be +5 and my acceleration be +9.8? I could, right? The problem with that doesn't arise so much here, but if we start throwing things into the air with positive being down and negative being up, right? It doesn't give us numerically anything different, but it just doesn't seem somehow to make sense that I throw something up and it's going in the negative as a negative velocity because I've chosen down to be positive. Does that make sense? Mm-hmm. So usually, down's negative. My acceleration, anytime I'm going up or down, is negative. My change in heights from up to down will be negative. I'll go from 5 meters to 0, which gives me delta x of final minus initial, or -5 meters. Is everybody good with that? If I go from 5 meters up to down. So now the two questions come up. How long is it going to be in the air? How fast is it going to be traveling as it hits the ground? Is everybody good with that? Mm-hmm. So I can say, is there a way to find the time? If so, what would it be, Allison? Which one do you think we might use?
What are we trying to find the x?
Trying to find time.
Trying to find time. Velocity final equals velocity initial 18.
Do we have final velocity?
No.
If we had it, it would work. So that's okay. So if that's not the choice, what is going to be our choice?
X equals initial position plus initial velocity times time.
Right? That position time equation, x equals x naught plus v naught t plus 1/2 a t squared. Does that make sense? So now I just plug my values in. My initial position is 5 meters. My final position would be 0. What's my initial velocity? 0. So what happens to this whole v naught t term? It goes away. So I end up with plus 1/2 of -9.8 times t squared. So now when I go to solve that, -5 times 2 over -9.8 equals t squared. and I take the square root of both sides, and I should get 1.01 seconds, I'm thinking. Is everybody good with that? So I can plug that into my table. 1.01 seconds. Now can I find the final velocity that it hits the ground with? A couple different ways. Probably the most obvious. VF equals V naught plus AT. So VF equals 0 minus 9.8 times 1.01, excuse me, negative 9.9 meters per second. Why is it negative? Because we set up down to be negative. We call the acceleration negative. It's going down. Down is negative. Anything going down is negative. My change in position is negative 5 meters. My velocity going down is negative 9.9. My acceleration negative 9.8. Questions there? Anybody? Are we good so far? So let's look at then another case where we, rather than falling down, we start with an object being thrown up at 20 meters per second. Is that a reasonable velocity to have, to throw something into the air? It's not reasonable? A machine to throw it that. Do we know how fast that is? Anybody? Can we figure it out? 20 meters per second. Let's say, gee, how many miles per hour is that? Because that's maybe something we understand. Right? So if we know there's 1,609 meters in 1 mile, and there's 3,600 seconds in 1 hour, it's like 44.8 miles per hour. Is that a reasonable throw? From any little leaguer in the world, that's reasonable. Yes or no?
Yes.
Most of them a lot faster than that. 10-year-old kids slinging at 70. Check out ESPN. There's a little girl does it from Texas. So definitely reasonable, 20 meters per second for my velocity. So what's going to happen to the baseball when I throw it into the air at 20 meters per second? Sam?
It's going to decelerate.
It's going to slow down or decelerate. And eventually what's going to happen to it?
Turn around and come back the other way.
Okay? Before it turns around and comes back the other way,
It's going to stop.
it's going to stop for the smallest, briefest time, the same way that cart on the ramp slides up, slows down, stops, and comes back down. Right? Make that all the way up, the ball's going to go up and come back down. But when we have a system like that or a situation like that, we want to look at what's going to happen when it goes up. And sort of like freeze frame it there and calculate stuff there and then talk about what's going to happen when it comes down. In two separate situations. So I have my initial velocity as 20. What about my initial position? Oh, it's a problem, isn't it? Right? Or it could be a problem. Right? Generally, the ground will be 0. I can make the ground be 0 and say that my initial position is x equals 1.5 meters, correct? I'll let it go here. good with that? And then when it goes up, it stops, it comes back down. I can catch it, or I can let it hit the ground, depending, usually, and in college textbook, you'll see the problems that involve, it lets it go at 1.5 meters above, and how long does it take to get up and hit the ground? All right? So now you're talking about whatever that maximum height is. When it comes back down, it's going to fall extra 1.5 meters. All right? For the most part, though, you'll really see like letting it go at position 0. How fast is it going when he catches it? Or she catches it? Or when it reaches the height that it left the ground from? All right? Does that make sense? Or reaches that same height. So you have x naught as being 0, although it doesn't always have to be the case. My final position will be what? Do I know?
No.
No idea. Something I'm going to try and figure out. My initial velocity, we already said, was 20. What is my final velocity on that upward stretch of motion going to be? 0? Everybody agree with that? It's going to go stop. Right? Really stops and then immediately comes back down. Doesn't stop and float up there. But for us, we kind of look at it as it stopped. It's up there hanging out. Let's calculate what we need to do. Then let's look at it falling down. Acceleration should be
Negative 9.8.
still negative 9.8. And the time it takes to get there, I don't know. So here I don't know time, I don't know position. Could I let my acceleration be positive 9.8?
Mm-hmm.
Which means this is positive, so what's my initial velocity got to be? Negative 20. And now in my head, it can become confusing. Right? Does that make sense? So if we think about down being negative, right? If I made down positive, my numbers would not be any different. The time it takes to get up there from negative 20 to 0 would be the same. The time it takes to fall back down would be the same. The velocity it had here, instead of being a negative value going up, it would be a positive value coming down. Right? It would all be the same, and numerically they would be the same. But like I said, in our head, to keep it a little bit clear, down, when we're talking about up and down motion, down's negative. Up is positive the same way it is on that regular Cartesian plane. Up is positive, down is negative. Right is positive, left is negative. It just sort of makes it simple for all of us to deal with. So in this case, which would we like to find first? The height or the time? Time, and how are we going to do that? Which says what? Vf equals V naught plus AT. So my final velocity 0 equals 20 meters per second minus 9.8 meters per second times time. And I get negative 20 over negative 9.8 equals t. And that should be 2.05, I think. 2.04 seconds. So I can plug that in here for time. Now can I find the height?
Mm-hmm.
Which way? Or is there more than one way, I guess, first thing?
Mm-hmm.
Okay, so the first equation being
Position time.
position time. Perfectly acceptable. My final position is what I'm trying to find. My initial is 0. 20 times 2.04 minus 1/2 of 9.8 times 2.04 squared. And I get 20.4 meters. We good there? Or I could use vf squared equals v naught squared plus 2ax, or 2a really y if I want to be technical, but I get 0 equals 20 squared minus 2 times 9.8 times x, and I get 400 over 19.6 equals x, and that's 20.4 meters. Either way works, gives me the same result. Anybody else got a question there? So now when I look at the downward motion. So when I go to my down components, what is my initial position when I talk about the downward motion of the ball? Right, it'd be my final position here, which was 20.4. So my initial becomes 20.4 meters. My initial velocity here is the same as which velocity in the up?
0.
My acceleration, still negative 9.8 meters per second. The time, we'll talk about the final velocity. Two things we don't know. The time, however, if it requires 2.04 seconds to go up and stop, how long should it require to come back to that same height? Same, more, or less? Less time to come back down. What is it that's making it stop as it goes up? The acceleration due to gravity, right? Now, when it gets up there and stops, does the acceleration due to gravity change?
No.
So it stays the same. So if it takes 2.04 to get up, would it make sense to make 2.04 to get back down? No. Let's look at that and see. How can I calculate the time to fall? Position time. Where my initial velocity is 0, my time is 0. My final position is 0. My initial is 20.4 meters minus 1/2 of 9.8 times t squared. So I get negative 20.4 over negative 4.9 square root equals t, and I'm thinking 2.04 is my answer. Oh, it's a miracle. Does that make sense? The same thing that's stopping it on the way up is going to be pulling it on the way down. That thing doesn't change. So the time that it takes to stop should be the same as the time it gets to come back to that same height. If I let it go here and say how long it's going to take to get back to the ground, I'd be, an extra 1.5 meters, which would be a couple hundredths of a second. Does that make sense? But if I go from one height back to that same height, the time should be the same. The total time in the air would take half that time to get to the top and half that time to fall back down. And those are the way the problems are usually looked at. Like I said, in the textbooks, you'll see this one. How long does it take to hit the ground after if it's released at 1.5 meters above the ground? What about my velocity? Same magnitude, same meters per second on the way down, more or less?
The same.
Who says the same? Who says less? Who says more? The rest of us have to say something. Other than I don't know. Well, let's look at it. Is acceleration any different than it was? Is the time any different than it was? So if it took 2.04 seconds to slow down from 20 to 0, does it not follow that it would take 2.04 seconds to go back from 0 to 20 if it's being pulled by the same thing? Those of us who are on this side of the room that are the I don't know crowd, does that logically make sense? Yeah or no? I still see some doubts over there. Like conceptually it doesn't. If it takes 5 seconds to stop by being slowed down at 10 meters per second every second, then I continue to pull it downwards at 10 meters per second. In 5 more seconds, would it not be going the same speed it was? And in fact it is, because you look at that, that should equal negative 20 meters per second. To come back to that same height. Now, like I said, if we were going to go add that extra 1.5 meters to get back to the ground, we're talking about a couple of hundredths of a meter per second difference. Not really worth getting excited about. Although, like I said, a college textbook, you'd see it. Because those intro college courses are, some of them designed to say, guess what? You're really not going to be an engineer. For chemistry, you're really not going to be a doctor unless you get through this class. It's just the way it is. So realize that going in. But the bigger picture, right? If it's accelerating by the same amount for the same amount of time, it should be going the same speed. 2 cars, exactly the same. Accelerate at 5 meters per second. Start at rest in 10 seconds, they should be going the same speed. That makes perfect sense to us. Any questions here? So we have some problems. Same thing, normally, right? A diagram, what's going on? Right? Whether it's dropping or going into the air. A little description so we can understand what's going to happen. When we put the ball into the air, what's going to happen? It's going to slow down until it stops at the top, then it's going to fall back and return to the earth. The acceleration during that time should be constant at negative 9.8. Then answer the questions we're asked, which really are going to usually involve find those things we don't know. I mean, if you just looked at it as forget the questions and just find the things that we don't know, then read the questions, you'll have the answers you need. Right? If you just said, well, I don't know this, let me find it. I don't know that, let me find it. Now what's the question say? Oh, how fast is it going when it hits the ground? We already have it. How long is it going to be in the air total? Well, there's the 2 times. Does that make sense? Or, as you get more comfortable, just answer the questions you're asked. Everybody good?